Well, happy Monday morning, everyone. I'm sorry not to be with you today. I am power play scheduling, but you are in good hands, I am sure. I'm going to go over the quiz that you just took with you quickly and then discuss the answers to your homework before getting into our learning target 5.3 a little bit more. So this is what your quiz looked like, and it said it was in acidic media. So I am going to go ahead and show you how I would balance this if I were you. First thing I see is that Mn, and the superscripts didn't come out here, but Mn is +2, and over here Mn is a +7, so that looks like an oxidation. I'm going to go ahead and write that down here. My oxidation is Mn +2 and MnO4 -1. My Mn's are balanced already, so all I need to do is balance everything else. So it looks like I'm releasing 5 electrons in the process here. It also looks as though I am short 4 oxygens. So I'm going to put 4 waters on this side, and that means I need 8 H pluses on this side. For my reduction, the Bi is what ends up being reduced. Over here it is a +5. Sodium is a +1, so that's +6 altogether, and oxygens 3 makes it, or 3 oxygens at -2 make it a -6. So Bi is a +5 over here and a +3 on this side. So my reduction is BiO3 -1 I'm just realizing that your sheet doesn't have this, which is good. So BiO3 -1, and so it's going from a +5 to a +3, which means we're going to need to add to that, and the Bi's are already balanced. We're going to need to add to that 2 electrons on this side. We are short 3 oxygens, so I'm going to add 3 waters over here. And then, to balance my hydrogens, I'm going to add 6 H pluses. And in order to balance out my electrons, I have 5 and 2, which means I'm going to need to multiply my top by a factor of 2 and my bottom by a factor of 5. And if I add them all up together, let's see, I would get 8 waters here and 15 over here, so that means 7 are left over. Two Mn +2s. So that's done. Let's see, I have 30 H pluses on this side and 16 on this side, so that means I have 14 H pluses left over. So 30 and 16. I have 5 BiO3 -1s. I have 2 MnO4 -1s. And 5 Bi +3. So there's your quiz. And then of course my 10 electrons up top and my 10 electrons in the bottom. So this is your final balanced equation. So there's your answer. Let's switch gears a little bit and talk about your practice problems that you had to do, number 26 and 28. So here's number 26 first. This is what 26 looks like. I'm going to go through this one with you. What I can see here is that my oxidation numbers that change are the copper, and then also -2, -8. My sulfur, so my oxidation that's taking place is my sulfur, so I'm going to go ahead and write that down, S2O4 -2, and S has a +3 there, and SO3 -2, it's +4 there. And the first thing I notice right off the bat is that my S's don't balance, so I'm going to go ahead and do that. Put a 2 right there, so I have 2 S's on both sides. And then what I can do is look at electrons, so I'm going from a +3 to a +4 twice, so I'm going to be losing 2 electrons. Then the next thing I'm noticing is that I have 6 oxygens over here and only 4 over here, so I'm going to add 2 waters. And then normally if this was an acid, I would also be adding 4H+, but I need to add 4OH- to each side because it's a basic solution. So that does 2 things for me. First, it makes this 4 waters, and since I have 2 waters over here, in total it just leaves me with 2 waters on this side. For my copper, I can ignore this NH3 because it stays the same over here. I just need to put a 4 in front of the NH3 because no oxidation numbers are really changing in this portion. It's just separating. So I'm just going to stick with Cu plus 2, turning into Cu with no charge or oxidation number of 0. And when I look at that, I see that I need to add 2 electrons to that in order for that to happen, which is very convenient seeing as I lost 2 up here. So that's it. I'm done with that part. My reduction is an easy one. So my oxidation was the hard work, and that's done, so I can add these together. No need to multiply anything. So I have 4 hydroxides, just 1 S2O4 -2. I've got a copper plus 2. Those electrons should even out. On the right hand side I have 2 SO3 -2. And my copper. Now if you're wondering about the NH3, that pretty much doesn't do anything except for get separated. Now you could include that down here if you wanted. You could tack that back on, NH3, 4 of them, but then you'd have to also remember to put it back up here separately. But this is more of like the net ionic equation for what's occurring. So either way is fine. Let's talk about 28. Whoopsie. There we go. So number 28, I have some Cl2 at a 0, and over here, -2 is a +5, and a -1 here. So I start with my oxidation, which is Cl2 over here, and that's turning into ClO3 -1. And the first thing that I notice is my Cl's aren't balanced, so I'm going to go ahead and put a 2 there. And what it looks like is happening is that 2 Cl's are going from 0 to +5. So each one is losing 5. That's a total of 10. I'm also short 6 oxygens, so I'm going to add 6 waters on here. And that would be 12 H pluses, but I'm going to add 12 OH minuses to that to make it 12 waters. But then I also have to remember to add 12 OH minuses on this side. I have water on both sides, 6 over here and 12, so I'm going to make this 6 waters. Now I'm going to go ahead and do the reduction. I've got Cl2. And again, I've got a problem with the number of Cl's, so I'm going to turn that into a 2. I am gaining 1 electron apiece, so for a total of 2. And that's all I really need to do. Looking at our electrons, I have 10 up here, so I don't need to do anything with that, but I can multiply this bottom part by 5. And in doing that, I end up with 12 OH minus. I am going to have a Cl2 up here. But I am going to add to that 5 more, so that's a total of 6. 1 here, and then the 5 down here. So I did that. I did the 5. And I got my 12 OH minus. Then over here, I'm going to have 10 Cl minus 1s. I'm going to have 2 ClO3 negative ones, and I'm going to have 6 waters. And then of course my electrons, 5 times 2 is 10, and then just the 10 up here. So that is my balanced equation. I'll move this a little bit so you can see it better. 12OH minus 1, 6Cl2, 10Cl minus 1, 2ClO3 minus 1, and 6 waters. So hopefully that went well. You're going to do some more of those today. But before you do any more balancing, and please remember that your LTA is over this tomorrow, we are going to continue where we left off in 5.3, just add a little bit to that information. So if you could get those notes out, and perhaps your sub will pause this while you do that until you are ready. All right, so I want you to forgive me because I erased our screen before I could write down exactly what we had placed for consider the following reaction. So this reaction may be slightly different than yours, and if that's the case, I apologize. You'll just have to change it just ever so slightly. But this is the reaction I'm going to go with now in your notes, so it'll be very confusing if yours is different. So I want you to take and make sure that your copper is +2 on the reactant side. And then on the product side, it has an oxidation number of 0, and then your zinc is happening the opposite. And we were labeling this picture of what's called an electrochemical cell. Where we have separated our oxidation and our reduction processes. So here we have our Cu with the 0 oxidation number, and then in solution we have some Cu +2, so that would be aqueous. This would be solid, so no charge, just a metal on the electrode. And same for your zinc. Zn is a 0, it's a solid, and then you've got in solution Zn +2. And we still have the salt bridge that we haven't talked about. But what I want you guys to see is that in the process of this reaction, what's happening is that the copper +2 is being reduced to copper 0. So we can write that down here as copper +2 becoming copper 0, and we're going to require 2 electrons to do that. So it's going to require 2 electrons to come in. On this side, and so what we have going on here is Cu +2, that's a reduction. Reduction is happening on this side. So this is our reduction electrode. So over here we must have oxidation, so we're going to have Zn becoming Zn +2, and then freeing up 2 electrons. So that's the same number of electrons, which is wonderful in this simple example to show that the electrons are being freed. So Zn is becoming Zn +2 in this situation, which means your electrons are going to be flowing this direction from what is oxidized into what is reduced. So if the electrons flow this way, then the copper +2 will be able to become copper. So those electrons will be used to make this Cu +2 become copper. So what you'll see happening in the process is that we are actually going to plate this copper electrode with more copper. So we're going to take Cu +2 and we're going to add on to that copper electrode right here. We're going to plate it with more copper than we had before. So this electron will appear to grow. Similarly, this zinc is going to become Zn +2. So what we're going to see is a deterioration of this electrode. It's going to actually get smaller because some of those zinc atoms are going to become Zn +2. The salt bridge is for the movement of non-participating ions. So the salt bridge is for ions that are not a part of this process to move. And the reason we need that is because when Cu +2 leaves and becomes Cu0, what happens is that some of this goes away. So the plus charge goes down. So we have a lack of positive charge. Because we have a lack of positive charge, a positively charged ion that's not involved in the reaction can move this way to make up for it. And that way the reaction can continue. Because if you have too much of one charge, then the reaction will just halt. It's too unstable. So if we want this to keep going, we have to have a salt bridge so we can make up for that with these positively charged ions. So when the Cu plus 2 moves into the copper, we have a lack of positive, so positive ions move in. On this side, when Zn0 becomes Zn plus 2, we have too much positive. And so the positive is already moving away, that's good, but what we want is some negatively charged ions to move into solution to counteract the additional positive charge. So the salt bridge is to balance the charges. It's a movement of non-participating ions. It allows them to flow back and forth. And our voltmeter is registering electron movement this way. That's a lot of information. I just want to do the basic setup there. Let's talk about an electrochemical cell in more detail now. So I want you to write down this definition. An electrochemical cell in general is an apparatus used to produce electrical energy through a redox reaction or vice versa. We might produce electrical energy or we might use it to make a reaction happen. What I want to just mention briefly before we're done here, oops, you can ignore that, is this thing called cell notation. So once you get that definition there, this is a general definition of an electrochemical cell, which is what you just saw. When you set up an electrochemical cell, what you can do is express this in a shorthand manner. So it's shorthand for describing activity in an electrochemical cell. So I just wrote a little note here because the way it's set up is that it's always done with the oxidation half cell first and then the reduction half cell second. So in our previous example, the species that was oxidized was the zinc. So the zinc went from Zn to Zn plus 2. It was oxidized. So this just shows, this line just separates our reactant from our product. So Zn started as 0, it was oxidized and became Zn plus 2. Then we take a double line to show the separation of the actual containers themselves, and we say, okay, well, the reduction that took place was copper plus 2 was reduced to copper 0. I don't know why I made those lines so much thicker, but they don't need to be. So the reduction half cell comes second. So it's like this happened, Zn became Zn plus 2, provided the electrons for Cu plus 2 to become Cu0. It's kind of like a story. Zn0 became Zn plus 2, which allowed Cu plus 2 to become Cu0. So we have oxidation first, always written, and then reduction, always second. And this is our separator of the two processes. So I have one last thing that I want to mention, and it goes back to your diagram, and that's some terms for those electrodes that we were talking about. So electrodes have specific names depending on what's happening at that electrode. And there's a handy little mnemonic that I know that helps me remember that. The mnemonic is, where is this? There we go. The mnemonic, I said demonic, oh my gosh, don't read too much into that. The mnemonic is an ox and a red cat. An ox and a red cat. This stands for oxidation. So whatever electrode oxidation happens at is called the anode. So wherever oxidation takes place is going to take place at what's known as the anode. Red in red cat is reduction, and that's going to take place at the cathode. So in this example, remember Zn was becoming Zn plus 2 and freeing 2 electrons that moved from right to left in this example. Right to left doesn't really matter, but in this example, moved right to left so that copper could go from plus 2 to 0. So since this is where oxidation happened, NOx, this is called the anode. The zinc electrode is the anode. And because this is where reduction happened, the copper electrode is called, excuse me, because this is where reduction happened, this is called the cathode. So those are specific names for the electrode depending on what process is occurring there. So an ox and a red cat. And that's all we're going to do today. You have some assignments involving balancing, and I hope that you'll get busy to work on that. And we'll talk more about electrochemical cells tomorrow after your LTA, but concentrate on that LTA for tomorrow. All right, talk to you later.